Hello. Today we'll be talking about areas of circles and sectors. And again, it's going to be pretty easy. I think most of this chapter is pretty easy, partly because it's not so abstract. Areas, arc lengths, these are real things. They're actually kind of useful too. Also, well, I guess there is no also. It's just a fairly easy chapter. That's all there is to it. We know the area of a circle. Let's remind ourselves. It's pi r squared. Every other time we had a formula for area, we proved it or derived it. For instance, we used the diagonals to find the area of a rhombus. Well, we showed why that worked. We didn't just throw out the formula and keep on going. Well, with this, that's kind of what we do. Just throw out the formula and keep on going. Why would that be? Well, here I've inscribed, this is a hexagon. More importantly, it's a polygon with n sides. In this case, 6. And here's the same. And they're both regular polygons. That makes it a lot easier. This is the circle inscribed in the larger polygon, and the smaller polygon is inscribed inside the circle. Now you can see that this polygon has an area much smaller than the circle. That should be intuitively obvious because we're leaving out this stuff. The stuff between the chords and the arc, that doesn't get included in the area. On the other hand, the area of this blue polygon will be larger because it includes the whole circle plus some of this stuff outside the circle right here. That's almost like a triangle, except that the third side is an arc and not a line segment. Well, what happens if I turn this into a octagon? Let's say a regular octagon. Instead of 6 sides, I've got 8. Or suppose I turn it into 20 sides. Well, if I increase the number of sides, that means the chords get smaller and smaller and smaller, because it still has to be, every vertex still lies on the circumference of the circle. We're not changing the fact that it's an inscribed polygon, we're just increasing the number of sides. So it could go from, in this case, 6, and just keep getting bigger and bigger. It'd be 20 sides, and then 100 sides. And I think you can see that if we get enough of these tiny little things, the difference between the area of this interior inscribed polygon and the circle is going to get smaller and smaller. And this area will get larger and larger, and there will be a limit to this area. I think I showed you this notation once before. Don't need to worry much about it. You're not going to see it on the state exam, and you don't need to know it until you get to calculus. Now, if we call this the area of the blue polygon, to say, if we call A sub B the area of the blue polygon, everything inside the blue polygon is, by definition, the area of the blue polygon. And what about the yellow one? Well, as the number of sides goes to infinity, this one goes up and up and up. This area goes down and down and down. If you were to graph it, the blue one will look like that. The yellow one will look like that. It'll come to, I'm not sure if you'd call that an asymptotic convergence. It probably is. We have a lower asymptote for A sub B and an upper one for A sub Y. And what does this turn out to be? That's the point where the area is pi r squared. This large limit will go down to pi r squared, and this one will go up. As they approach each other, when they become equal, that's at the point where the area singular is pi r squared. That's as n goes to infinity. Anything short of infinity, the equality doesn't hold. That's where calculus comes in. If that seems bizarre to you, well, of course it seems bizarre. When people introduced calculus a long time ago, that was Isaac Newton or another guy named Gauss. I think his first name was Frederick. If If you're European, you would say Gauss. Put it out there first. If you're English, you say Newton. I'm American, so I really don't care. But this idea of limits and limiting values, that's actually fairly complicated. You really shouldn't understand much of what I'm saying here. You might get the rough idea that this area gets smaller and this one gets bigger. And that's really all I'm trying to get you to understand. Why? So if you understand that, then you can see why we don't really prove this in this class. It's more than we'll really understand how to do right now. And it's kind of confusing. Although, when you get to calculus and have this explained, and spend several weeks just working on limits, it'll become much easier. Well, we know the area of the whole circle. And let's say this is R. This is the same. This was the center of the circle here. We know the area is pi r squared. Wow, that's a really bad looking pi. Oh well. What's the area of some piece of the circle? Like, if I go like that and cut out this little piece here, this here, what's the area of this? I couldn't tell you. That's not going to be in this class. Suppose we section this circle up differently. For instance, suppose I slice it like it were a pizza. That sector we can figure out, because this has an angle that we can measure, or it'll be known. The entire circle has an area of pi r squared. Now, how much of the circle is this little section? Well, suppose I drew a straight line, or tried to. Forget it. Suppose I draw a straight line that's supposed to be a continuation of this, which is a radius. So I've got a diameter here. And I ask you, what's the area of this section over here? I think you'd immediately say, well, it's half of that, because this diameter just cuts the circle in half. If this is half of the circle, then it makes sense that it would have half the area. And you'd be right. It works that way with areas, just like it did with arcs. If I said the circumference of this thing, it's 10 feet all the way around, how far is it from here over to here? I think you'd immediately say 5 feet, even if you hadn't seen anything from the last section. You would just automatically cut it in half. Sector areas work exactly the same way. You may have intuitively just spotted that this was half of the circle, so it must be half of the area. But if you gave it a little more thought, you might have said, the circle is 360 degrees. This is 180 degrees, which is half of 360. So I'll take half of the area, and that'll give me the area of this sector. And you'd be right there too. So that's what we're going to do. For this sector here, we'll say a sub s, the area of the sector. Well, that's just the area of the circle, pi r squared, times the fraction of the circle, which this would be. And what fraction of the circle is this? Well, it's the same as the fraction of 360, which is alpha. Alpha over 360. That's exactly what fraction of the circle you have here. So if alpha were, say, 36 degrees, pardon me, 36 degrees, then you'd have 1/10 of the circle, and this would be pi r squared over 10 would be this. See, yeah, it's very simple, very much like arc length. So let's work some problems and see how easy this really is. Well, here we have some more error analysis, and they tell us that the area of circle Z is 48 square feet. And all we have to do is figure out which fraction of the whole is made up of this sector here. I believe this is the sector of which they're trying to find the area. I'm not sure what in the heck he was doing here. In the first place, I don't believe a student would do anything like this. I think a congressman might after 5 drinks. Even a congressman wouldn't be this dopey. But after a few drinks he would be. And since they're rarely ever sober, I guess it could have been a congressman doing this at almost any point in his career. It's hard to say what in the world he was thinking of. I guess maybe he subtracted, I don't know what he subtracted here, 75 from 360, and wow, this is really a mess. I think you can spot exactly what he really should have done. It's the fraction of the circle made up by this sector is 75 over 360. The area of the whole circle they already gave us. We don't have to compute it. It's 48. So assuming you want the area of this sector, you take 75 over 360 and multiply it by 48. Now this is the equation that he should have been solving. We might even be able to do this without a calculator. Let's see. Divide that by 12, and that's 4, and that's 30. And so far so good. So we get 4 times 75. That's 300, right? Over 30. Well, 30 divided by 3, I think it'd be 10. And 48 square feet, so this answer would be again feet squared, that's 10 feet squared, or 10 square feet. This is just, well, who knows? This is what you should have done. What he should have done, rather. I'm sure you wouldn't have made a mistake like this. You take the fraction of 360, which is 75, and that of course is 75 over 360. Multiply by the whole thing, and that tells you what fraction of the area you've got. Actually, that gives you an actual number. This tells you what fraction of the area you have. Then you multiply the area by that fraction, and that tells you what actual area you have. It's probably a better way to look at it. Now for this one, naturally they want us to add up a bunch of areas. And we can do that. To find the whole area, we can find the area of this triangle, or pardon me, rectangle, this rectangle, and then this sector of the circle. And we know we can do that from a previous theorem, which tells us that so long as the areas don't overlap or have any gaps, we can add them all up. That's exactly what you would have thought was true if you've never even taken this class, isn't it? Well then, let's see here. This is a right angle, this is a right angle. We've got rectangles here. That's cool because then we know. In fact, we got a square up here. That's even easier. So we know that this, which is actually a radius, is 3.5. And we got 3.5 over here for this rectangle. So these are both radii. So they should have exactly the same length. If this was different here, then we wouldn't really have a circle. And we'd be in trouble. But we have a circle, so we're not in trouble. This is a 90-degree angle. I think I even mentioned that when I was pointing out how we figure out sectors of circles. I think I used 180 actually. But 90, that's obviously 1/4 of the whole circle. 90 over 360 is 1/4. And I think you can see that if you just considered this to be like a diameter and finished off the circle, well, the next 90 degrees would give you the next half of the circle. The next 90 degrees would give you 3/4 of it, and you'd finish it off with 4/4. So this is 3.5 squared times pi divided by 4. So the area for the circle is pi times 3.5 squared. Now we have an area for a square here, and that's going to be 3.5 squared. The rectangle, that's easy too. Area of the rectangle is just 7 times 3.5. Oops. That looks better. Now if we add all these up, we'll have the whole area. I don't know about you, but I'm going to use my calculator for this one. So we lay these all out. And this circle area needs to be divided by 4, because this is 90 degrees, and it would be 90 over 360 times the area of the circle. That's 1/4. So that's all you needed to know. That's why I said you can do this in your head. 1/4 of the area, 9.62. The area of the square, 12.25. It's 3.5 squared, and this one is 24.5. Well, if we add that all up, and when I add them up, I get 46.37, which looks pretty close. And that, of course, is supposed to be feet squared, because they gave us all our dimensions in feet. So that was really, it took a while, but it was really pretty easy. You just had to take the area of the square, 1/4 of the area of a circle, and the area of the rectangle. Now this problem isn't too hard, but pay attention, because I remember seeing one exactly like this on one of the standardized exams. I think it was a PARCC exam. So I think it's a safe bet you're going to see almost exactly this problem on the standardized test. What they want you to do is find the areas of the shaded part. At least I think that's what they asked for. That's right. So each of these circles have a radius which increases by 2 feet at a time. In other words, the smallest one has a 2-foot radius. This is a 4-foot radius, 6-foot, and 8-foot. And I guess we could label those. Let's see here. This would be 8. This is 6. This is 4, and this is 2. What we're going to do, I think the easiest way would be to take the whole circle, subtract this inner circle, add back in this circle, and then subtract this circle. That sounds a little weird, but it's all we're doing is, in the end, we'll just be taking this one and this one. But remember, we have to take, suppose we just wanted to know this, say, rim. All we would do is take this circle with the 8-foot radius and subtract the area of this circle with the 6-foot radius, and we'd be done. But what we have to do is do that twice. So if you prefer, we could do it that way also. We could find this one by taking the area of the 8-foot circle and subtracting off the 6-foot circle. That'll give us this. Then we take the area of this whole thing and subtract off this. They amount to the same thing when you lay out the equation. It's just a matter of how you arrange the equation, really. So let's do it. See how easy this really is. This is, the area of this is pi times 8 squared. The area of this is pi times 6 squared. Now let's see here. The area of this, and we want the whole shaded area, so this gives us the outer one, but we have to add in the other one, and that's pi 4 squared minus pi 2 squared. Like that. But we can get rid of the parentheses if we wanted to. And what we've got is pi times, in fact, we could even factor out the pi. We can pi times 8 squared minus 6 squared. Sorry. plus 4 squared minus 2 squared. So we got 64 minus 36 plus 16 minus 4. Well, if you do all that, I think it's easier to, as I say, factor out the pi. Use that at the very end. Otherwise you get a whole bunch of weird numbers here. Instead, if you factor out the pi, you get a whole bunch of really easy numbers. 64 minus 36 is 28. 16 minus 4 is 12. 28 and 12 is 40. Pi times 40. I always use 3.14, but if your calculator has a nice simple pi button, you can use that too. Either way, you should get about 125.6. That would be the area of this. And you have something like this. It's like the rim formed by a circle. It's called an annulus. You could probably draw another one with all the stuff on the side, inside of it. Hang on. Well, I won't win any awards for artistry, but if you pretend that this is a circle, and then we just cut out this circular section and right inside of it, this outer part here is called an annulus. I think that's what it's called. And I double check that. Yes, this is called an annulus. And now, from what we just did, it should be easy to see that the larger circle, say, has radius r, and the smaller circle, this yellow line here, has radius r. Well, what's the area of the annulus? Pi times big R squared minus little r squared. In other words, this is little r, this is big R. You take the whole circle and subtract off the area of the little circle. And that's all we did in here. And it might be easy to just spot right off the bat what this person's doing wrong. And let's lay out some equations, and we can get something strong to hang our hat on here. The arc lengths of two arcs, and this is in the same circle, is 2 to 1. So what that means is, let's see here, let's say well, we have that the measure of one arc is double the measure of some other arc. We'll call it AB and EF. What's the relationship between the areas of these two arcs? Well, remember, the measure of an arc is the same as its central angle. So if the central angle for AB is alpha, then the central angle for EF is 2 alpha. Given this, how would we compute the area? Well, for this section, it would be, I'll do it down here, alpha over 360 times the whole area, which we didn't actually, I don't think they gave us the area, did they? No. That's that times pi r squared. What about this sector here? Well, we're talking about the same circle now. So the area for this sector would have to be 2 alpha over 360 times pi r squared. If we take the ratios, in fact, just to make this super simple, why don't I pull out the 2? 2 times alpha over 360. I pull out, I mean, put it outside the parentheses. Pi r squared. Well, if I take, let's say, the area formed by a sector with central angle alpha divided by the area formed by central angle. 2 alpha, that'll be this over this. And all this stuff is the same. This is exactly the same as this. Alpha over 360 pi r squared. Alpha over 360 pi r squared. But there's a 2 out in front. So this whole thing is just 1 over 2. Or if you do it the other way, a sub 2 alpha over a, well, that would be 2. So you don't square. If you double the angle, you don't square the two angles. You don't square the two different areas. If I take a sector and double the angle, I double the area. I don't square the area. This is a little bit different from, say, rectangles and squares. Remember when usually you have to square whatever you do to one thing. But this is different because we've already expanded an area. And when we say that we've doubled the angle of a sector, what we really mean is we've doubled the size of the sector. We didn't quadruple the size of the sector. If all we did was double the size of the sector, we multiplied the area by 2. When we're working with rectangles, when we extend sides, that's different because the area is the product of the two sides. Notice in this, when we're computing areas for sectors, the angle just enters in here once. So if this is the area, or when we double the angle, then we just double the area. It's actually so simple I'm having trouble finding other ways to say it other than whatever you do to the central angle, you do the same thing to the sector area. Now this one looks a little tough, but it's not that bad. What you have to remember is that arc lengths, they move along with the radius. In other words, if you double the radius, you double the arc length. Well, what do we got here? We have the same angle. These two sides, they tell us, are radii of the larger circle. So the point where they intersect, right about here, I guess it would be. That's also the center of the small circle, which doesn't matter very much. What does matter is this ratio here. This large arc is 3 times the small one. So the large radius must be 3 times the small one. In other words, we've got that, put it over here, R1. I'm going to call that the small radius. If R1 is the small radius, then R1 plus 8, that's the large one, equals 3 times R1. The large radius here is R1 plus 8, but it also has to be 3 times the small one. We know that from the ratios of the arc lengths here. This is 3 times the small one. Well, if we subtract 3 times R1 from each side, we get that 2R1 equals 4. Pardon me, 2R1 equals 8. And R1 equals 4. That's good, because to work this problem, we need the angle and the radius. We had 2 variables that we didn't know. Instead of setting up super complicated equations, which is one way to do it, we could have set up a much more complicated equation to solve for, say, R1 in terms of alpha, if we want to call our angle here alpha. We could do that and use up about half a page and arrive at the conclusion R1 equals 4. I think this approach is a bit easier. Now that we've got R1, we pretty much have everything we need to find the area. Almost. We still don't know the angle, do we? But that's okay. We can find the angle now. For instance, 2 pi r1, that's all the way around this big circle, times the appropriate fraction of that circle will give us the 10 meters. Well, that means that alpha over 360. But we know R1. We can replace it with 4 and get that 8 pi times alpha over 360 equals, well, they gave us that. We know the arc length, we're just going backwards to figure out what the angle was that it came from. Now we just solve this. We put all this stuff over on this side and end up with an alpha. If we rearrange this, we get that alpha is 360 times 10 over 2 pi times 4. And we can start doing some canceling here. We can scratch out the 4, change the 360 to 90. In other words, divide top and bottom by 4. And we can get rid of the 2, either change this to 45 or this to 5. What the heck, we'll make this 45. So we end up with 450 over pi. Now, with alpha, rather than come up with a number, we just insert it here, 450 over pi over 360. This is the angle. Well, 450 over pi times pi, the pi's cancel, and we get 450 over 360 times the large radius squared minus the small radius squared. 8 and 4 is 12, so our large radius is 12. Our small radius is 4. Well, 12 squared is 144, 4 squared is 16. 144 minus 16 is 128 times the 450 over 360, cancel the zeros, 45 over 36. That's the same as 5 over 4, right? 5 times 9 and 4 times 9. And, well, parentheses might make this more obvious. Times the 128, and that's 160 meters for the shaded region. This part here would be the area of the entire annulus all the way around. I think I showed you that earlier. Just the big R squared minus the little r squared, all times pi. But we have to take the fraction of that, which is represented by this sector here. And that sector is 450 over pi over 360. I think this is like 140, 145 degrees, something like that. Which kind of makes sense. That looks like a pretty big angle, doesn't it? So this problem looked a little tougher than it really was. The important thing to spot was that our arc lengths change linearly with our radii. In other words, they move right along with it. You double the radius, you double the radius, you double the arc length. Cut the radius in half, you cut the arc length in half. Cut the radius by 1/3, then cut the arc length by 1/3, then you've cut the radius by 1/3. Which is exactly what happened here. We decided that this had to be 1/3 of the whole thing. So if we make this 4, the whole thing is 12, and this is definitely 1/3. That's the part that made this problem pretty easy. You spot that, and then you get 4. Now you don't have two variables anymore. You just got the one. It's pretty easy to find alpha. And then you got this mess down here that's not really that bad. I like this problem because it's extremely practical. I don't know how much cooking you guys do yet, but I make these calculations almost every time I cook. I don't believe I've ever followed a recipe. They never call for the amount of what I want to make. It says, oh, it makes 15 servings. Well, I don't want 15 servings. I want 5. That happens all the time. Well, they want, we got a recipe for a 6-inch diameter tortilla. Now we want one with a 12-inch diameter. And we're going to assume they're the same thickness. we haven't even talked about volume yet. So we're assuming that the only thing we need to worry about in terms of how much dough we need is the area. We're going to have to assume that because we haven't even talked about volumes yet, so we couldn't do it if we included volume. What is the area of a tortilla with a 6-inch diameter? Well, it's pi r squared, and r is 3, isn't it? Or 9 pi. What about this one? I haven't worked out an exact number yet, because I think what we care about is the ratios. We want to know how much more than 1/4 cup, or what should we multiply by? What should we multiply 1/4 cup by to get enough dough for the 12-inch diameter one, which is pi times 6 squared, or 36. Well, we got 36 pi versus 9 pi. So 4 times the 9 pi is 36 pi. And what we need to do is have 1 whole cup of dough. And if we flatten that out to the same thickness as we did with our 6-inch tortilla, we'll end up with the pretty much identical 12-inch tortilla. And that's about it.